going to be pretty easy. It's not hard at all. You could say it's very basic. Aha! All right. Strong and weak bases are just like strong and weak acids, except there's no Hickel, Hibber, high. There's nothing like that. Strong bases are ones that dissociate completely. So they're group 1 hydroxides. Sodium hydroxide, potassium hydroxide, rubidium hydroxide, lithium hydroxide. Weak bases are going to be things like ammonia or things with a lone pair that it can contribute to. Basically, here's what you need to know. Group 1 hydroxides, those are strong bases. All the other things that might be bases, we're not going to worry about. They're all going to be weak. So if it's not a strong base, then it has to be weak. All right, a little bit of vocabulary. Polyprotic acids are just where something has more than one hydrogen. In this example right here, carbonic acid, yeah, it gives up one. And that has one equilibrium state because the first one comes off easier than the second one. So you could write an equilibrium expression for this. It would be H plus and you write HCO3 minus over, what do you think it would be? That's right, H2CO3. And that would be Ka1. Ka2 would be the bicarbonate ion down here turns into hydrogen ion and carbonate ion. So for a polyprotic acid, let's say you had 3 hydrogens. Well, you would have 3 Ka expressions. We want to talk about buffers today. Buffers is just an extension of a weak acid or a weak base. We've always started with just a weak acid or just a weak base. But what happens when you start with some weak acid, say acetic acid, but you also start with some of its conjugate? You also start with the conjugate base or the conjugate acid. So acetic acid and acetate. What happens when you start with both? The idea of a buffer is you have a little bit of an acid and you have a little bit of a base, and they're centered on some common ion. So it could be hydrofluoric acid and fluoride. That would be a buffer, or acetic acid and acetate. A buffer has to consist of a weak acid and its conjugate, or it could be a weak base and its conjugate. So ammonia and ammonium. That would be an example of a buffer as well. If you throw some acid in there, ain't no big thing because the base can handle it. If you throw some hydroxide in there, not a big thing. The weak acid can handle it. So the buffer is able to maintain a constant pH or a fairly constant pH. Very small changes in pH will happen if you add acid or base to it. Here's an example. This is a buffer made up of the acid right here and its conjugate down here. Don't worry about the sodium. It is this ion right here which is the conjugate of the acid. That's the common ion we want to worry about. So the pH of this is 4.74. I'm going to add a bunch of solid sodium hydroxide to it. And when I add solid sodium hydroxide to it, the pH barely even increases. It only goes up 4.76. So that's exactly what a buffer does. Resists a change in pH. When they ask you what is the buffering capacity, the buffering capacity is just how much acid or base is in there. So you could have 0.1 molar acetic acid and acetate ion, or you could have 0.2 molar acetic acid and acetate ion. Which one has the greater buffering capacity? The 0.2 molar, because it has more of the acid and its conjugate. If you want to think about this in terms of Madison's landscape, go by any subdivision built within the last 10 years and they all have a pond. And if you look at the pond, you can go, it's capable of absorbing this much runoff from the neighborhood. And if you absorb that much runoff from the neighborhood, then that will keep the creeks and streams and the drainage system in Madison from overflowing during a major rainstorm. Now, does that mean it always works? No, because conceivably you could overload that thing. You could get so much rain that you totally fill the pond and it totally overflows its banks, and then the pond doesn't do you any good. Same thing with a buffer. It can handle a certain amount of acid or base, but you can get to a point where you overwhelm the buffer and then it just can't do its job anymore. I want you to take out your equation sheet and find this equation. It's called the Henderson-Hasselbalch. The Henderson-Hasselbalch is useful for calculating buffer solutions. You can also do it with an ice table, that's fine, but this is the quick and easy way to find the pH of a buffered solution. Or, if you're looking for a given pH, what is the relative proportion of base to acid that you need in order to achieve that pH? Let me show you an example of a buffer problem. They're going to give you an acid and its conjugate, or they're going to give you a base and its conjugate. We write an ice table just like we did before, but let's just make up some numbers. Let's say that the concentration of the HF started out at 0.2. And the amount of F was not quite as much. It started out at 0.1. And they want to know, what is the pH going to be at equilibrium? Well, we know HF is a weak acid. And we don't care about this part right here. And we know that there's 0 hydrogen ion at the beginning because it didn't tell us we added any. So this is going to go down by X. This is going to go up by X. And this is going to go up by X. This is going to be 0.2 minus X. This is going to be X. And this is going to be 0.1 minus X. The only difference from what we have been doing is this part right here. We usually start out with 0 of that. This time we've started out with some of that. So what would our next step be? We'd write the Ka expression. Ka is equal to the concentration of hydrogen ion times the concentration of fluoride ion over the concentration of HF. Notice all the same that we have been doing. We're going to neglect the X. We're going to say 0.2 minus X is the same thing as 0.2. We're going to say that 0.1 minus X is pretty much the same thing as 0.1. And so when I substitute into my Ka expression, I'm going to get X times 0.1 over 0.2. Now what do I need? I looked up my Ka value for HF, and it is 6.6 times 10 to the negative fourth. When I solve for X, I get X is equal to 1.32 times 10 to the negative third. And if I scroll back up, I will see that my H concentration is the value of X. So if I know my hydrogen ion concentration is 1.32 times 10 to the negative third, all I have to do is take the negative log of that, and I get a pH value of 2.88. So you can work buffer problems using this ice table, or you can use Henderson-Hasselbalch to solve this very same problem. So let's see what that looks like. Henderson-Hasselbalch is pH is equal to pKa plus log of the conjugate base over the acid. So let's just plug in the numbers that we got. So the pH, we don't know that. The pKa means the negative log of the Ka value. The Ka value was 6.6 times 10 to the negative fourth. The negative log of 6.6 times 10 to the negative fourth is 3.18 plus the log of the conjugate base, which if you remember was 0.1 molar, that was given to you in the problem, over the amount of acid, which started out at 0.2. When I solve the problem using Henderson-Hasselbalch, I get 2.88. When I solve the problem using an ice table, I got 2.88. It works the same. You should know what happens when you take a log of a number. If A is 0.1 and HA is also 0.1, then the log of 1 is 0. You know that that goes to 0. So if the amounts of A minus and HA are the same, then pH is just going to be equal to pKa. If the amount of conjugate base is greater, so let's say that A is 0.2 and HA is 0.1, the log of 2 is going to be a positive number. So the log of any number greater than 1 is a positive number. The log of any number less than 1 is going to be a negative number. When there's more of the conjugate base than there is of the acid, the pH will actually increase past the pKa, When there is less conjugate base than there is acid, the log of that is a negative number. That means the pH is going to go down below the value of the pKa. You should never have to do logs in your head, but you should be able to know that the log of a number less than 1 is negative and the log of a number greater than 1 is positive.